in this talk, I'm going to talk about AIRS. It's something about deep reinforcement learning, how to explain it. Actually, the student who did this work, the first author, he cannot be here, unfortunately, so I'm presenting on his behalf. And this is a joint work with a group of great researchers from 5 different institutes. I will not name them all, but they are great. Okay, first I want to put together some background about reinforcement learning. I feel it's still kind of a new concept for the security community, although it has been in machine learning for a while, right? So reinforcement learning, basically, as you can see in the figure on the right, we have basically 2 components. One component is the environment, basically contains some like setups, right? What you're gonna do with the goals. That's everything was in the environment. And then we have agent. The agent's goal is to finish a task in the environment, right? For example, let's say we are playing a ping pong game, and then the ping pong, the table is gonna be the environment, and then the players are gonna be the agents, right? And in this environment, agents at each time, it gonna take some action based on the current state. For example, for ping pong again, it just I need to take action based on where is the ball, right? So that's what agent gonna do. And after agent take action, the environment gonna kind of observe like that action and then translate to the next state. At the same time, the environment gonna reward the agent with the how good was the action, right? So it's like ping pong is if you get a ball, you're gonna right. If you hit a ball, probably gonna get a positive reward. If you miss the ball, you're gonna get negative reward. And the goal of the agent basically just try to maximize the amount of reward that the agent can receive. So that's the basic setup of this about this reinforcement learning. And then recent days, there are some like researchers doing some excellent research about how to use reinforcement learning in security applications. There are actually many of them. For example, malware detection, some network APT detection. Here I'm gonna use this blockchain selfish mining as an example. Again, some background about blockchain mining is like, I will keep it very simple in the sense it's like, we can imagine in this case, there are just 2 miners. And the miner who just trying to broadcast the blocks on the longest chain, and who was able to do this will get rewarded, right? In this case, we can say the blue miner gonna get 3 rewards. The red miner only get 1 reward because the other block was not on the longest chain. And then actually, some miners can play some strategies, right? There's 2 types of miners. One, we call them honest miner, just, okay, every time I found a block, I broadcast it. And then there's some like selfish manner, try to play some strategy to maximize this reward. For example, in this case, we take the red manner as the selfish manner. So he or she can play some strategies like, okay, I found 2 blocks, I just hide it to myself without broadcasting it. And then I observe the main chain, and then I broadcast it once I feel like I can override the main chain, which can kind of help me get a higher reward. And in this research, the researcher just try to build some reinforcement learning agent to play the game, right? To replace the selfish manner, try to learn some policy, okay, what I should do, what strategy I should play to maximize my reward. And then comes to some explanation, right? So you said we know deep learning is hard to explain. That's already pretty complicated. And reinforcement learning is even more complicated because think about deep learning is just a 1-step decision. It's either classification, cluster, all those 1-step decision. But here, reinforcement learning, we need to do a sequential of decision to finish one final goal. So making the same explanation job even harder. So we look into the existing explanation. What they try to do is they try to actually just extend the explanation of deep learning classifier to reinforcement learning setup. It's like at each step, the reinforcement learning agent, the deep reinforcement agent is just a neural network. It can observe the current state and then give an action. And then people try to explain, okay, why my agent take this action as a state, right? It's just something similar to your classification model taking an image of cat, and the model tell you, okay, this is a cat, and then why. So it's kind of explain the model step by step. That's what, so basically explanation can just be, okay, in this case, okay, the model tell me I'm gonna take the first action, and then what specific component or what specific subregion within the current state, basically is the status of current chain, make the agent take the current action. But the problem with this type of explanation is that, okay, I know why my agent take individual actions at each time step, but overall, I don't have kind of a more global or overall understanding of the strategy, right? For example, let's say in this case, after few steps, the selfish manner was able to collect a lot of rewards. And then I want to understand why, right? As overall, what's the strategy was played by the selfish manner that make it get so many rewards. And basically it's question similar to, okay, what are the critical moves made by this selfish manner that needed to get those many of rewards, right? Similarly, let's say you're playing Go games, you win in this game round. We want to identify, okay, what are the critical moves made by the reinforcement learning player that was, let's say, AlphaGo, right? So was able to make the AlphaGo wins over some professional human players. And then by looking at those critical moves, we should be able to have a better understanding about, okay, what's the strategy played or strategy learned by the reinforcement learning agent. And then with all those motivations, I think our task become pretty straightforward. Is say, hey, I have this trajectory of a reinforcement learning, taking, I don't know, like 100 steps, for example, and then I get this final reward. I want to know, okay, I want to identify what are important moves. So basically, our strategy at a high level is we collect a bunch of rewards, a bunch of trajectory, and then we collect the reward of each trajectory, and then we try to approximate this trajectory with some explainable model. It's kind of like turning the reinforcement learning stuff into some like a explainable kind of like a classification problem. And then we can design some explanation model or interpreter model to do this classification and then identify the critical step. So here's all our model design. Since the input is actually different from, right, like a typical classification, let's say image classifier or natural language process. So we design a kind of like a customized model to do this. The high level idea is something like this. It's like our model input is a set of states, it's a sequence of states. So we need some model can process this sequence of states that actually capture the time dependency and then output some low dimensional representation, which is better for us to approximate some like linear regression or descent tree or those explainable model. So the first module is a recurrent network. And then we have another module that try to further reduce the dimension of the outputs of recurrent network. And then we have this module output, which we call theta module. It's pretty important. It's like this theta module try to make, it's a neural network, but we'll try to kind of adding some constraint, adding some regulation, make it work like multiple linear models. You can imagine we try to do some like a local approximation, like multiple local approximation for a neural network, make a model locally linear. And finally, we can just run this linear regression, and this, since this theta works local linear and give you a data point, which is the sequence or trajectory, we should be able to tell you, okay, which one is more important because it's linear. And here is kind of like a high-level view about our trajectory, about our training and explanation process. Basically, objective function, two parts. First part is how well you can approximate the trajectory. Second part is we need a constraint to make it run locally linear. And after we're fitting the model, we get everything trained, parameter trained. We just fit in a trajectory, and then by looking at the theta, ranking theta, we should be able to know, okay, which state is more important. And of course, we run some evaluation. The first evaluation is kind of standard. We want to know, okay, the fidelity of explanation, right? It's like how well you can explain. It's like how faithful is your explanation, whether explanation truly reflect the original policy learned by the agent or not. So we design some experiment and we design some metric to do that evaluation. I will not go into that detail because of kind of like time limit. And then I think the more interesting thing is like how we're gonna do with the explanation, right? It's like after we get explanation, how we're gonna do with it. Basically, of course, you can understand agent policy. For example, in this case, this trajectory where you can see the selfish manner collect like more rewards in honest manner, and then we identify, okay, this override step is the most important one. By looking at this step, you can see clearly why the agent was able to collect more reward, because the agent just override the main chain when it has a huge advantage. When the margin is a little bit high, it do the override. On the upside side, it's like we also try to explain some trajectory where the agent wasn't able to collect a good reward. For example, in this case, we highlight, okay, this is the step, right? So basically, it's just the agent was doing something opposite. It's like the agent cannot wait for that long, right? So agent just, okay, I have one advantage over the main chain, I just do the fork or just override. In that case, I cannot maximize my return. So basically, this story tells us, okay, be more patient. Help yourself for a little bit longer time before you try to broadcast things, right? So, and then we kind of do some tweak to the agent policy. We try to fix the policy, and then we do some evaluation to say, you can see the kind of amount of reward collected by the agent before and after we do the patching we can say it can collect actually more reward. So that's one example about how to use explanation to do something else, right? So that's one example is just try to fix the weak policy. We have another example in our paper is we actually find some bugs, design flaws in the reward, which is also interesting, but I cannot cover. So please go and read it. It's gonna be pretty fun. Okay, finally, just some like a normal conclusion. Basically, we can say, hey, by fitting the trajectory, we can explain the reinforced learning. We can identify some critical moves, which is good, right? And then of course, we propose AIRS, which is designed to do this. Finally, I think it's the most interesting part is I will demonstrate. But after getting the explanation, it's not done yet. There's so many interesting things we can do with explanation. Yeah, that's pretty much what I want to talk today, and I hope there are some good questions. Thanks.